So again, the very infamous Fibonacci series to understand recursion. And in this, recursion applies like you all know what a Fibonacci series is. Whatever a number is, last two sum of last two digits produces the next number. For example, 0 plus 0 and one other digit, and this produces 1 because 0 plus 1 is 1. Then 1 plus 1 is 2, this produces 2. 1 plus 1 1 plus 2 is 3, this produces 3. And better ignore the, no, I'm not sitting on a railway track, this is my fan behind, so if you want you can ignore it. And 2 plus 3 gives us 5, 3 plus 5 gives us 8. So this is the series. And how we can code it using recursion, what we need to do, I'll just tell you what we need to do. We need to break this whole bigger problem into a smaller problem. And the smaller problem here is these are the base cases. These are the base cases which are the what you can say minimum reduced one. Like you cannot go beyond them. For example, in our Fibonacci series, the base case goes like f of 0 and f of 1, because less than, if you'll go f of 0, what you'll need for, like, according to the definition, you'll need -1 plus -2. So there is no negative comparison of this minus. Similarly, for 1, what you'll need 0 plus -1. So this does not give 1, but adding 5 and 8 definitely gives 13. So the base case would be f0 and f1, and in f0 we know that it will be 0, and f1 it will be 1, like Fibonacci of 0th number and Fibonacci of first. This is a 0th number, this is the first number, so this will be like this. Just a second, let me clear. So what I'm trying to say is, basically we need to divide this in a smaller problem. We have already did this. It's f of 0 and f of 1. These are two the base cases. Now comes the recursive thing. Now comes the recursive thing. Recursive thing would be calling out the function. For example, if we have Fibo function, calling out the function and adding last digit and last to last digit, like these two. Just a second, I'll explain this with an example. Like we have 55. So to form 55, for example, 55 is, I guess, 10th. This is first, second, third, fourth, first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. Yeah, 55 is the 10th digit of Fibonacci series. So if someone asks n is equals to 10, which means you need to give the value of 10th number in Fibonacci series, it will be 55. So how 55 would be created? Adding last two digits of 55, which are 21 plus 34. This is how it was created. So n minus 1 is 34 and n minus 2 is 21, which is last digit and second last digit. Adding these two gives us 55. So the code which we'll use here is, just a second, yeah, this is the basic code. Like this is the main, this is a driver code, just taking input output, and this is the logic. For base case, we have already defined if n is equals to 0 and n is equals to 1, return n because for 0 we have 0 obviously, and for 1 we have 1. So 0 digit is 0, first digit is 1, second digit is also 1, third digit is this. Similarly, we have 10th digit equals to 55. So recursive case goes like, first digit will be f n minus 2. First in the sense, for 55, 21 and 34. This is first digit, this is second digit. Adding these two would give us 55. So first digit would be n minus 2, because this is 1 and 2. This is 2 placed behind of this. Second digit will be n minus 1, which will be 34 here, and final result will be just adding these two. So you can just comment hold this out, and what, like, I'll just code it. What you can do directly is you can return the final result, which is Fibo n minus 1 and Fibo n minus 2. Like you can just directly add here and return. You do not, just a second. This one is commented out. No? You need not to declare final and first and second. You can directly just, this will, I'll just explain this. Uh, what this will do, yeah, in 55, this thing, n minus 1 will add 21, sorry, this will add 34, and n minus 2 will add 21. So adding these two, this will go recursively. Like for example, if we'll take 13, so n minus 1 of 13 is 8, and n minus 2 is 5. So 5 plus 8 gives you 13. So you can find any number of Fibonacci series in this. Thank you.